This is the video for section 11.10 on Taylor and Maclaurin series. And here's the point. So in the previous section we found some power series representations of functions based on the geometric series. And what we want to do now is we want to construct power series representations for other functions, ones that you can't get from the geometric series. And the basic idea is the following. So if we assume that we start with a function that can be represented by a power series, so we start with some function that's represented by the series n equals 0 to infinity, cn times x to the n, and I'll write out a few terms here. Up to the fourth term. So if this is our assumption, then from what we've done in previous sections, we know that we can take the derivative term by term. So for instance, the first derivative, I just take the derivatives of the pieces that I have over here. The constant term disappears. I get c1 plus 2c2x plus 3c3x squared plus 4c4 x to the third, and so on. And the second derivative similarly. And then the third derivative in the same way. Right, so I have that the third derivative is 6 times c3 plus 24 c4x, and so on. And when I plug in x equals 0, I just get 6c3, because all these other terms have an x in them, so when I plug in x equals 0, they disappear. And when I solve this for c3, I can write that as the third derivative evaluated at 0 divided by 6, which is the same thing as the third derivative at 0 divided by 3 factorial. So the thing to note here is that the third coefficient is gotten by taking the third derivative evaluated at 0 and dividing by 3 factorial. So what we find in general, using this technique, is that when the function is represented by this power series, that the nth coefficient can be written as the nth derivative of the function evaluated at 0 divided by n factorial. And so the series that we started with can be rewritten as the sum n equals 0 to infinity of this coefficient times x to the n. And this series is called the Maclaurin series for the function. If we do this more generally by using instead of x equals 0, we use x equals a, then we would find the Taylor series for the function is the summation n equals 0 to infinity f to the n evaluated at a instead of at 0 divided by n factorial times x minus a to the n. Okay. And we'll do an example on the next page. So for example, if you are asked to find the Maclaurin series for the function f of x equals ln of 1 plus x, what you have to do is you have to find those coefficients that we had before. So we're going to look for Cn is the nth derivative of this function evaluated at 0 divided by n factorial. And we'll do that in several steps. So first of all, you have to take the derivatives. So my original function is ln of 1 plus x, and its derivative is 1 over 1 plus x, which I'll rewrite as 1 plus x to the minus 1 so that it'll be easy to take derivatives. The second derivative is then negative 1 plus x to the minus 2. The third derivative is going to be negative 2 times 1 plus x to the negative 3. So that's the same thing as positive 2 1 plus x to the minus 3. So what you can see here is that as I take higher derivatives, what I get is I'm going to get alternating signs. I'm going to get products of the old coefficients with the old exponents and then powers of 1 plus x. So the next one, the fourth derivative, I'll have 2 times negative 3, 1 plus x to the minus 4. Okay? And in general, if you continue this for a few more steps, you'll see the pattern. The nth derivative is going to be negative 1 to the n minus 1 times n minus 1 factorial divided by 1 plus x to the n. So that's my 1 plus x to the minus n. So next what I have to do, as I wrote over here, is I have to plug in 0 into these derivatives. So f of 0 is ln of 1, which is 0. F prime of 0 is going to be 1 to the negative 1, which is 1. F double prime of 0 is negative 1 to the negative 2, which is negative 1. The third derivative at 0 is 2. The fourth derivative at 0 is going to be negative 6, and so on until we find that the nth derivative at 0 is going to be negative 1 to the n minus 1 times n minus 1 factorial. And so when I take my Cn, I'm going to divide that by n factorial. So for instance, C0 is going to be 0 over 0 factorial, which is 0. C1 is 1 over 1 factorial, which is 1. C2 is negative 1 over 2 factorial, which is negative 1/2. C3 is 2 over 3 factorial, which is 2 over 6, so 1/3, and so on. So we get that Cn is negative 1 to the n minus 1 times n minus 1 factorial over n factorial. And we've played with enough factorials, hopefully by this point, to see that this cancels the n minus 1 factorial cancels the factorial from the n factorial, so we get negative 1 to the n over n. And so we find that the Maclaurin series in this case is the summation n equals 1 to infinity. And the reason we start at 1 is because this 0th coefficient that we found was 0, and the remaining coefficients are negative 1 to the n over n, and then x to the n. Now, what you should notice is that I'm not making any claims that this function is the same as the series. Okay? And we're going to talk about that in just a minute. What we need to do before we do that is to find the radius of convergence of this series. And maybe I'll let you do that as an exercise. The radius of convergence, we use the ratio test for that, just like we did in the section on power series, and we find that r equals 1 in this case. Now, in order to understand the question of when does a function equal the sum of its Maclaurin or its Taylor series, we need to go back to some questions about partial sums. And for that we'll use a definition that's going to be useful for the rest of the chapter. So the nth Taylor polynomial of a function f of x is, the notation is Tn of x, so it's going to be a function. The t is for Taylor, the n is for taking the nth Taylor polynomial, and this is the summation k equals 0 to n of f to the k. So we're going to take the kth derivative, evaluate at the point A, which is going to be the center of this polynomial, divide by k factorial, and multiply by x minus a raised to the kth power. The Maclaurin polynomial is what we get when we use a equals 0, and so there we get the summation k equals 0 to n f to the k evaluated at 0, like we did in the previous example, divided by k factorial times x to the k, because we're using a equals 0. And what we'll see in a little bit in this section and a little bit next section is that this is actually a really good approximation for the original function. And once we have the Taylor polynomial, we have the nth remainder, and this is the error between the original function and the nth Taylor or Maclaurin polynomial, depending on what you've been asked to look at. Okay. So for example, if we do the third Maclaurin polynomial for the function we were playing with before, then it's just the summation k equals 0 to 3 of those coefficients that we had, negative 1 to the k, let's see, k minus 1 over k times x to the k. And when we write that out, we end up with, sorry, that should of course go from k equals 1 to 3, right, because our Maclaurin series started with k equals 1, so we end up with here x minus 1/2 x squared plus 1/3 x cubed. And in order to understand why or when this is a good approximation, we need two things. We need the following fact, and this is just a reinterpretation of what we already know for partial sums. So if the limit as n goes to infinity of Rn of x is 0, and this is for all x with absolute value of x minus a less than r, then f of x is the sum of its Taylor series for all x's satisfying this inequality. So the upshot here is that if we want to understand when f is represented by its Taylor series, what we need to check is we need to check this limit as n goes to infinity, and that makes sense. And we have a particular tool for checking this limit that we'll see on the next page, and that is Taylor's inequality. Taylor's inequality is one that you're going to have to memorize, and it says the following. So if I take the n plus first derivative of my function, evaluate it at x, and take the absolute value, and I know that that is less than or equal to some fixed number m whenever my x's satisfy absolute value of x minus a less than or equal to d, and here d is just some number, then I get to conclude that the absolute value of the nth remainder is less than or equal to m divided by n plus 1 factorial times x minus a to the n plus 1. And this is true for x's satisfying the same inequality. And I'm going to use this in an example to show that the Maclaurin series for cosine of x represents cosine of x for all x values. Now, in order to do this, we're going to use a really handy limit that I'll explain to you. And this is a really good limit to have for all computations involving Taylor's inequality. So when we look at e to the x, its Maclaurin series is summation n equals 0 to infinity 1 over n factorial x to the n, and this has radius of convergence infinity. And that means that this series converges for all x. So the test for divergence tells us that no matter what x value I plug in, when I take the limit as n goes to infinity of the nth term of this sequence, I get 0. And this is something we'll use in just a second. So, when I want to understand the Maclaurin series for cosine of x, and this is written out in the textbook, we actually don't need to know what the Maclaurin series is. What I need to do to use Taylor's inequality is I have to find an m that satisfies this inequality for all x's. And this is going to work really nicely for cosine because the nth derivative of cosine is either plus or minus cosine or plus or minus sine, depending on what n is, right? We know that when we take derivatives of sine and cosine, we just keep getting plus or minus sines and cosines back. And so we get to conclude that the absolute value of the nth derivative of this function is always less than or equal to 1, because plus or minus cosine and plus or minus sine are always bounded in between 1 and minus 1. And so this is the value we use in Taylor's inequality. And what we get to conclude from Taylor's inequality is that the absolute value of the nth remainder is less than or equal to 1 over n plus 1 factorial times x to the n plus 1. And we should put absolute value around the x there. Now, of course, this remainder is an absolute value, so it's greater than or equal to 0. And the tool that I wrote out up above, here, tells me that down below, when n goes to infinity, the limit of this right-hand piece is 0. And of course, the limit of 0 is 0, so by the squeeze theorem, we get to conclude that the absolute value of Rn of x as n goes to infinity is 0. And so by the fact on the previous page, we get to conclude that the Maclaurin series for cosine of x actually represents cosine of x for all values of x. Okay. Now, this is a very, very, very long section, so I'm not going to do any more examples, but I want to point out some things that you can find in the textbook for this section. So if you look at examples 3, 4, and 9, these are examples, more examples about finding Maclaurin and Taylor series and their radius of convergence and verifying that they actually represent the functions that they come from. Example 5 uses this along with some old techniques in order to do another example using the derivative. Example 6 does the same thing with multiplication. In Table 1, and the ebook that I have, this is on page 786, this will give you a list of some useful series. That can be found using this technique. And then in example 10, you can see an example that shows how to use this to actually evaluate a sum that we didn't know how to evaluate before. Example 11 shows how to use these Taylor and Maclaurin series to find an integral. And example 12 shows you how to use this to evaluate a limit. And for those of you who are in engineering, when you get to the course on differential equations, some call that Calc 4, using these power series, these Maclaurin and Taylor series, is going to be incredibly important for solving differential equations. So this is something that you're going to need to be able to use a couple of semesters down the line. All right, so this is the end of the unfortunately long video on section 11.10.